Okay, we'll go ahead and get started. This is chapter 5, radio signals and equipment. I'm recording this on May 6th, 2021. So we'll go ahead and get started. Um, the title page from the instruction manual points out the topics we'll be covering, and I'm probably going to hit some of these more, and I may not even hit some of the other ones. But we'll have a look at basic signal concepts, and it's a partial review because we went over some of these ideas in the technician study groups. Take a look at oscillators, mixers, multipliers, and modulators, and primarily not only take a look at what they do, but why we need them and how they're used in the radio equipment we use to do the things we need to get done with the signal processing. Then we'll take a look at some fundamentals of transmitters and amplifiers, some receiver fundamentals, and then the chapter has some information on installing an HF station. So basically what we're trying to do when we're using amateur radio is that we're trying to take some sort of an audio signal. And audio is the range of frequencies that we can hear. And the audio signal can be a voice, it could be a digital signal, but generally the signals operate, the information is contained in frequencies from 1 to 4 kilohertz. And the way voice, and in some cases you can do digital this way as well, the way it operates is that the microphone's really a transducer that takes the sound energy from pressure waves in the air, picks those up and converts that to electrical signal that follows the sound. So if you speak into a microphone and you had an oscilloscope or a pretty fast chart recorder on it of some sort, then you would see the intensity of the sound wave or the voice that it's hearing. And when the volume is high, you'll get a high signal. And then as the volume dips down, you get a low signal. So we get this time signal that is a representation of the sound or the digital signal that we're trying to send. So, if you're not too familiar with this, you may just wonder, well, why don't we just transmit this audio signal directly? I mean, we've got it here in electrical form. Why don't we just amplify it and push it out an antenna and avoid all the other stuff? Well, if you go through the exercise of calculating what size antenna you would need in order to do something like that, we took this formula that we saw first in the technician chapter, where the length of an antenna in feet, you can get a rough estimate by dividing 492 by the frequency in megahertz. So if we had an audio signal of 4,000 hertz or 0.004 megahertz, based on this calculation, we need an antenna 23 miles long. So, that's a little crazy. It'd be a little tough to drag that around with an HT. So the things we're going to be looking at are devices and techniques that are used to take this audio signal, which is very low frequency, and we really can't do much in way of transmitting it through the atmosphere because of the antenna size. And somehow we're going to have to take this information that's contained in this waveform and get it to a frequency so that we can transmit it from a reasonably sized antenna. And depending on other conditions that may be in consideration, would determine which band we'd try to transmit on. And then on the other end, when we're receiving, we've got to figure out how to take that higher frequency signal that we're receiving and extract the signal information from it, the audio, because what we are interested in here in this case in an audio transmission is what was said into the microphone. So somehow we're going to have to get this received signal sorted out and into a format that we can listen to and understand it. So that's what all these things we're going to be looking at here in the next few slides are meant to do. So, and this is a little bit of a review, or should be a little bit of a review from the technician study group that we went through, or you went through, or possibly you did this on your own. But the idea of modulation is how we take the information that we're trying to transmit, which in our case, if we're looking at a voice signal, is that waveform that we were looking back here. So one way we could do it would be to have a high frequency signal generated of a fixed frequency, and then impose that waveform on the amplitude of that signal. And then we could transmit that. And then at the receiving end, we need to be able to receive the signal and then extract the envelope of the amplitude modulated signal so we can get that noise or the sound out and make it useful. So that was one of the first modulation techniques we looked at, was amplitude modulation. And we see this not only in ham radio, but AM radio broadcasts. Like locally, we have the 1 AM station, 1420 AM, and that stands for amplitude modulation. So this is how they transmit their radio programs. And then another way we can do it is, rather than adjusting the amplitude proportional to the sound signal that we're trying to transmit, we could adjust the frequency so that as the level of the voice signal changes, we can change the frequency. You can see here, this is a higher frequency waveform than this, so we can modulate the frequency to give us that same waveform there. And yet another way would be to do phase modulation. This is done quite a bit in the digital modes, where you can see we have a sine wave going here, and you would expect it to continue up and then come back down, just like the preceding sine waves. But in order to detect or send a change in the signal, the modulation has occurred, say going from a 1 to 0, we reverse the phase. And then that tells the receiving station, if this was a 1, this is a 0. And we can modulate the phase to transmit that information. So let's take a look at bandwidth. And we'll start off looking at analog signals. Now, what this graph is, it's a measure of the signal power that's being received. And on this axis is the frequency. And normally you look at a signal, like these are time signals. The horizontal axis is time. So, you know, however many seconds this takes, time's continuing, and the signal varies as a function of time. In this case, we're looking at the signal as a function of frequency. What does the signal look like during in the frequency? And what this comes from is that there's a theory that you can take any time signal that has like a voice signal that has variability in it as it tracks the voice, and you can duplicate that signal with an infinite series of different frequency sine waves. So what you're looking at here in a frequency plot is what the different frequencies are in the signal at that particular point in time. And if you remember, we looked at a band scope on single sideband, and you were looking at the side lobes, the lower sideband and the upper sideband, and you could see that the waveform here on the lower sideband was changing with the voice. So it was transmitting the signal in time. When you looked at it in terms of the frequency, the as the voice changed, the sideband changed, and that's how the information is set. Now in straight AM modulation, like the radio stations and the commercial radio stations, and there's a mode in ham radio too of amplitude modulation. What's transmitted is the carrier signal, which is the base signal. It would be the frequency of this. This is called the carrier signal because it's carrying the information with it. So in terms of frequency, the carrier signal is transmitted, and then both sidebands are transmitted, both the lower and the upper sideband. And so what is actually carrying the information is the variation in this sideband, either the upper or the lower, and they're both pretty close to being identical. So they kind of have redundant information. So when you look at an AM signal, you'll see a lower sideband, a carrier frequency, an upper sideband, and there'll be references to the upper sideband bandwidth, and that's the width of this signal here. The lower sideband, obviously the width of this signal, and then the carrier frequency, which carries no information. So the different modes that can be used in amateur radio have different restrictions on it in terms of the bandwidth that you can use according to limits set by the FCC. And if we go back here and look at this, you can see, for example, that if you're transmitting AM, you're using twice as much bandwidth as lower sideband, or if you only transmitted the upper sideband. And that's why the ham radio community uses single sideband, which could either be lower sideband or upper sideband, because the only thing that is transmitted is the sideband signal. The carrier is suppressed, as is the other sideband. So just by going from AM to single sideband, we cut the frequency bandwidth in half, so we have more efficient use of the frequency spectrum. You can get more conversations in a set range of frequencies with a single sideband than you can with AM. So that's why they put these limits on. For AM voice, the 6 kilohertz bandwidth. Amateur television, I have no experience with that, but it's set at 6 megahertz. Single sideband voice is 2 to 3 kilohertz, and that's because it's narrower. It only uses half the bandwidth of AM. Digital, using single sideband, there's range there of 50 to 3 kilohertz. CW is a very narrow band mode. One of its attractions is it uses minimal bandwidth, and one advantage of having a minimum bandwidth is you pick up less noise because you can filter out all but what you need to hear from the CW. And then FM voice is authorized 5 to 16 kilohertz of bandwidth. So in order to modulate our audio signal with some sort of sine wave, we have to be able to generate a continuous, constant frequency, constant amplitude sine wave. And what is used to do that is a circuit that's called an oscillator. And what it'll do, it'll be designed such that it'll generate a fixed frequency, constant amplitude sine wave that you can use to modulate the voice signal. There are also variable frequency oscillators where this frequency can vary by the design of the circuit. Two of the kind of basic oscillator circuits that have been around for a long time, you may hear reference to, are the Hartley oscillator and the Colpitts oscillator. And you can see they have a transistor with some reactive components, inductors and capacitors. And if you remember when we're talking about reactance, the big thing with capacitors and inductors is that they don't really dissipate energy. They store energy and then re-release it at different times of in the circuit. So this inductor will have current flow through it. It'll build a magnetic field, and then as the polarity of the signal reverses, that magnetic field collapses, causing current to flow into the capacitor. That increases the voltage. So this oscillator is essentially taking energy and just shuttling it back and forth in the form of magnetic field. It's storing as magnetic fields and electric fields on the capacitor. So the Hartley oscillator uses two inductors and a capacitor to do this, and the Colpitts oscillator uses two capacitors and an inductor. So it's this storage and releasing of energy going back and forth with a high enough gain amplifier that you can sustain the constant frequency and constant amplitude output of the oscillator. And there was another point I was going to make, but I forget what it was. Probably wasn't that important. Okay, we'll come back to it. Maybe I'll remember later, maybe not. So this is a sine wave oscillator. There are other types of oscillators, a couple that you may run across, one called relaxation oscillators and astable mode vibrators. And what they produce rather than a sine wave is a square wave or a rectangular wave. And those are used a lot in digital circuits where you want some sort of constant frequency, constant amplitude, square wave or rectangular wave. And then there's another type of oscillator you may run across called a sweep oscillator. And what that does is it'll generate a sawtooth. Rather than sine wave, it'll ramp up linearly and then drop. It'll ramp up linearly and go to zero. Or it could ramp up and ramp down. And you can change the frequency and the amplitude by changing the components in the circuit you design. So that's an oscillator, and that is what gives us this fixed frequency, sine wave or square wave, depending on what is needed. But we need that oscillator to kind of get us the baseline frequency that we need to be at to transmit. And then this diagram out of the book is just showing how an oscillator could be constructed with any type of amplifier. These are used operational amplifiers. If you remember in the last chapter, we talked about operational amplifiers or op amps that have a symbol similar to this. They're used in building oscillators because they have a very high gain capability, and then you provide some feedback to make the oscillator work. So it doesn't have to be a transistor, but there does have to be an active device in an oscillator. By active device, I'm talking about either transistors or op amps. You can't generate an oscillating signal with just passive components because what the active components, whether it's the transistor or the op amp is doing, it's making sure that there's sufficient energy brought back into the system because you do have resistive losses in these passive reactive devices. And over time, what would happen, the oscillator would just get slower and or lower in magnitude if you weren't replenishing the system energy with either the transistor or an operational amplifier. So you always need an amplifier of some point, some part in an oscillator. Okay, next thing we're going to look at is called a mixer. And what a mixer does is it takes an input signal coming in, say, for example, RF, and it multiplies it in the schematic or in the circuitry with a local oscillator. You know, we just talked about an oscillator, so we've got an oscillator sitting out here generating sine waves at some frequency, and then by multiplying it with the input signal, we get an output signal that is the sum and the difference of the two frequencies.